This is a continuation of our discussion about the nature of electricity. We will now discuss some other concept about electricity. This includes electric current, electric potential, electric resistance, the Ohm's law, electric power, and power laws. The movement of electric charge is known as electric current. Therefore, any moving charged particles could consist a current, but it is most commonly moving electrons. Electric current is the rate of flow of electrons in a conductor. Rate means a measure of quantity per unit time. Therefore, electric current can be defined as the number of electrons passing through a given point per unit time. Electric current is measured in SI unit of ampere, with capital letter A as the symbol. 1 ampere is equal to 1 coulomb flowing at a given point in 1 second. That means that if there are 6 quintillion, 250 quadrillion electrons that pass through a given point in a conductor for 1 second, that is equivalent to 1 ampere. 1 ampere is also equal to the amount of current flowing with an electric potential of 1 volt in a circuit with a resistance of 1 ohm. For a current to flow, there must be conditions that must be satisfied. First, there must be a source of electric potential that pushes the electrons to flow. There must also be a complete circuit around which electrons are able to travel. This is the function of the switches. It effectively cuts the continuous flow of electron in a circuit, thereby stopping the electron flow. There are 2 types of current, the direct current and the alternating current. Direct current is a type of current that only flows in one direction. Example of a direct current is the current being supplied by a battery. When the current leaves the negative terminal of the battery, it will go in a single direction and just return to the positive terminal. The voltage waveform of a direct current will look like this. It is constantly in a positive cycle with constant voltage depending on the voltage of the battery. The alternating current, on the other hand, is a current that changes direction in cycles as the electric potential of the source changes. Alternating current changes direction at 50 or 60 times per second. That is, the flow of electrons goes forward and backward 50 to 60 times per second along a conductor. The electricity that we get from an electric socket being supplied by an electric company is alternating current. Accordingly, this type of current is easier to transmit in long distances. The voltage waveform of an alternating current looks like this. The flow of current changes from positive cycle to negative cycle, changing also the voltage as the flow of current changes, from 0 voltage to maximum voltage and then back to 0 again, doing it twice in a cycle and several number of times in a second. In the X-ray tube, we have to be familiar with 2 types of currents. They are different but are connected. We have the filament current, which is the current being supplied to the filament of the X-ray tube for it to boil off electrons. When these electrons, boiled from the filament, travel from cathode to anode by application of a very strong potential across the tube, it then becomes the tube current, responsible for X-ray production. The filament current of about 5 to 7 ampere will generate a tube current in milliampere. The next one is the electric potential. Electric potential is a driving force which moves the electrons along the conductor. Electrons flow from abundance to deficiency and will continue to do so as long as that difference exists. Electric potential is therefore defined as the ability to do work because of the separation of charges. Electric potential is measured in the SI unit of volt, with capital letter V as the symbol. 1 volt is equal to the potential difference that will maintain a current of 1 ampere in a circuit with a resistance of 1 ohm. The electric potential across the X-ray tube is what propels the electrons to move from cathode to anode even in the absence of a conductor. High potential difference in kilovoltage or thousands of volts is necessary. Therefore, the voltage supply of 110 to 220 volts by the electric company must be converted first to thousands of volts before being supplied to the X-ray tube. The next concept is the resistance. Electric resistance is the impedance to the electron flow. It reduces the flow of electric current through the circuit and converts it to heat, which is the reason for power loss. How much resistance is applied is dependent on the type of material used as a conductor. Electric resistance, therefore, is a measure of how the device or material reduces the electric current flowing through a circuit. The SI unit of electric resistance is ohm, with the symbol omega. 1 ohm is the resistance in a circuit when 1 volt maintains a current of 1 ampere. As mentioned, the material used as a conductor determines how much resistance is given. The following are the factors that affects resistance. First is the material of the conductor. Conductor materials will definitely have less resistance compared to insulators. But even within the conductor materials such as copper and iron, there are still differences in the amount of resistance they give. Copper offers less resistance than iron, and so copper is usually the conductor of choice in electric circuit. The next one is length of the conductor. Long conductors have more resistance because the electrons have to pass through a longer path. The thickness of the cross-sectional area of conductors is another one. Small cross-sectional area has more resistance. This is probably the most variable of all factors, and therefore, electricians consider the type of appliances used in determining the thickness of the wire to be installed in houses, buildings, and offices. The last factor is the temperature. As the temperature rises, resistance also rises. And as the wire applies more resistance, it will generate more heat. So it is a never-ending process until heat becomes fire. This is probably the reason why during hot summer days, there are more house fires due to faulty electricals. Electric current, electric potential, and electric resistance are all related, and their relationship is shown in Ohm's Law, which states that the potential difference across the total circuit or any part of that circuit is equal to the current multiplied by the resistance. The formula is V is equal to I multiplied by R, where V is the electric potential in volts, I is the electric current in amperes, and R is the electric resistance in ohms. An increase in current or resistance, or both, would have a corresponding increase in voltage or electric potential. But current and resistance have an inverse relationship. If the voltage remains constant, an increase in current would mean decrease in the resistance or vice versa. Next is the electric power. It is the rate at which energy is transferred. It is actually more familiar to us as the amount of electricity being supplied by the electric companies or used by electric appliances. It is defined as the rate per unit time at which electrical energy is transferred by an electric circuit. It is the product of current times the voltage. The SI unit of electric power is watt, with the symbol of capital W. 1 watt is equal to 1 ampere of current flowing through an electric potential of 1 volt. The last topic is the power loss. We know that in the conservation of energy, that energy is not lost but can only be converted to other forms of energy. So in effect, electricity as a form of energy cannot be lost, but is converted to another form of energy. The lost energy in a circuit is converted into heat energy. But this can happen even as the current is being transmitted through power lines or cables. This is because of the electric resistance. To keep power loss to minimum, the following can be done: reducing the current flowing within the cable and reducing the resistance. This ends our presentation for today. I have posted additional learning materials for you to understand better how electricity works. Thank you so much.